Welcome everyone to the Joy Room. We have a great lineup of speakers ready to go. First up is Derek Elkins. Derek has been interested in applying theory and particularly category theory to Haskell for a long time. From calculating monads with category theory in 2009 to being one of many co-authors on the very recent Profunctor Optics, a categorical update. Today's talk is more of a programming language theory talk, though there is still a bit of secret category theory. Take it away, Derek.
Thank you, Francisco. So this talk is essentially two little talks put together, and then a third final section that will be relatively brief, but just kind of talking about what happens when we combine them, or just more of just suggesting ideas. I don't have a lot of answers in that section. So the first part is quotient types, and I talked about quotient types a few times. There's actually articles on my site for both of these things. And so one of the main motivations for quotient types is enforcing invariance statically in a way that doesn't require information hiding. And part of that secret category theory is that this is a dual concept in the categorical sense to the notion of subset types. So this is the main thing I want to talk about, since this is probably most interesting and relevant to the Haskell community, and probably closest to something that you could potentially use more or less today, though it's not something that you can just grab GHC and start using, but I'll talk about that a little bit. Behavioral reflection, on the other hand, is dramatically different. This is research that came out of the Lisp and Scheme community from the late 1980s on, and this is like the Scheme community is known for wanting to have like a minimal language with a lot of expressive power, and behavioral reflection is arguably the ultimate form of this. It essentially lets you redefine the language from within the language. It makes everything first class, but it totally, if Haskellers are worried about like exceptions in mutable state making it harder to understand a program, this totally wrecks program comprehension. It's literally possible to use behavioral reflection to change, say, a call by value language into a call by name language, and back just when some function is executed. So I'll talk a little bit about how that actually can be done. And then, since this is a Haskell conference and I'm a Haskeller, the combination will be using quotient types to kind of tame behavioral reflection. So it's not nearly as, it's not nearly as semantics destroying as it could be. So first is quotient types. And before that, I want to talk about like why we use abstract data types like data.set, or what's another good one? Data.map would be a good one, or pretty much any abstract data type. The main two reasons are information hiding. So if we want to change the representation of a type, we can just swap out a new representation, and as long as we don't expose these details, we only work against the abstract data type interface. We don't actually have to change any of the code that uses it. And the other main reason we use abstract data type is enforcing invariance. We want to make sure that if we have a set and it's represented, say, with a list of values, we want to make sure that that list doesn't have duplicates. Maybe that list is sorted, and we want to ensure that that invariant is always held, and then we can exploit that invariant in our implementation. So before going on to quotient types, I want to talk about subset types because they are a little more natural and easy to understand. And as I said, they're dual to quotient types. And so this is a fairly straightforward idea. You have some type T, and you have some predicate on types. This might be in a dependently typed language, or it could be using something like liquid Haskell. So subset types are refinement types. And basically, this subset type says this, given a value x of type T, we only want to consider those values that satisfy this predicate P. And the simple example is the set of, or the type of non-zero integers would just be integers restricted to those that are not zero. So that's straightforward, I think. And so consuming subset types are easy. A value of type non-zero is just an integer. It just happens to exclude integers that are zero, but that doesn't matter to you as a consumer. But to produce it in general is hard. You have to produce a value of the type T, in this case integer, and you have to show the compiler, you have to convince the compiler that the value you provide actually satisfies the predicate. In a dependent type language, this might be providing a proof term. In liquid Haskell, this is handled by a SMT solver or some of the kind of high order and reflective features that has. So I think this idea is pretty intuitive. And one of the reasons I want to talk about this idea and quotient types as well, another little bit of category theory, is that given products and subset types, so products, normal pairs and whatnot, you can get what are all categorical limits, all finite categorical limits if you have finite products. And so many constructs are either limits or co-limits. And so understanding records essentially in subset types allows you to understand all finite limits. Similarly, understanding coproducts, so sum types like either, and quotient types lets you understand all co-limits. So these two types, subset types and quotient types, kind of round out what kind of limits and co-limits can be made, and that's filling in a gap, I think, in programming language theory and more programming language practice. So quotient types are unfortunately not nearly as simple as subset types. So they're typically written as a type T divided by, or the slash, and then some kind of equivalence relation here represented by the tilde kind of symbol. And so the intuition behind a quotient type is that you have T, but instead of considering two values of type T equal when they are the same value, we're going to say they're equal when they are related by this equivalence relation. And I'll go in a bit more detail, but dual to subset types, producing values of a quotient type is easy. Any value of type T is a value of the quotient type. So there's nothing that needs to be done there. But consuming them is hard. If you want to consume a value of a quotient type, you need to ensure that you satisfy or you respect this equivalence relation. So before that, let's actually talk about what an equivalence relation actually is. And so it's just a binary predicate, essentially, that satisfies these three rules that are fairly straightforward. It just says if x should be related to x, just like x should equal x. If x equals y, essentially, y equals x. And if x equals y and y equals z, then x should equal z. That's the intuition. We're just generalizing this to an arbitrary equivalence relation. And so any relation between a type and itself can give rise to an equivalence relation. We can just say, well, if x is related to y, then we'll just add y is related to x to the relation. And if x is related to y and y is related to z, we'll just add x is related to the z to this relation. This can be expressed, for example, by like a simple data log program, or even like a recursive query is kind of the idea. But most of the time, you can just directly define what would be, in this case, the reflexive symmetric transitive closure of a relation. But a lot of times it's convenient just to talk about a relation and then assume that the equivalence relation we want is generated from it. So special type of equivalence relations are called effective equivalence relations. And they're ones where we say X is related to Y if and only if we have some function H that maps maps X to some value, maps Y to some value, and X and Y are related only when those values are the same. The intuition here is that you have some kind of like normalization function that can map X and Y to some normal form, and then X is related to Y if those normal forms are the same. So for example, with rational numbers, you can reduce to remove common factors, and then the two pairs of numerator and denominator, once you remove all the common factors, are equal only if the original rational numbers were equal. So in many cases, effective equivalence relations are easier to work with. For example, if you wanted to make an abstract data type of rational numbers, you could use this reduction to reduced form as a way. Like you can either, anytime you create a rational number, you could just always keep it in reduced form, or you could allow it to be a general form, but then anytime you actually try to do like get the numerator, get the denominator, you actually reduce to the normal form. But it's not always possible, or at least practical. It depends on the language. It's not always possible to find these normal forms. And so this first example of unordered pairs is an example where it's not an effective equivalence relation in this sense. So you want to say a pair XY is equivalent to a pair AB if X is equal to A and Y is equal to B. So if XY equals AB, then they're going to be considered equal. Or if XY equals BA, so if we swap them, we'll also consider those equal. And so in this case, we want to consider two pairs equivalent if they have the same elements, regardless of the order of the elements. Second example is rationals. And again, this equivalence relation is, in this case, pretty easy to write. This doesn't use the kind of reduction to a normal form, but is a fairly simple example. Modular arithmetic. This is like X mod Y equals, or X mod N in this case equals Y. So if X and Y differ by some integer multiple of N, then we'll consider them the same. This is like clock arithmetic. An interesting example, well, the first example is actually kind of interesting. And actually, this is a generalization of the first example, is multi-sets or bags, which if X's and Y's are two lists, we want to consider these two lists equal or equivalent if they have the same elements regardless of order. So if they're sorted and then they're equal after being sorted, then we'll consider them the same bag. So this makes multi-sets with different numbers of elements, duplicate elements, different. But if they have the same number of elements in different orders and the same elements, then they will be considered equivalent. And this is an example of an effective equivalence relation as well. A more involved example, that's, I think, one of the reasons I kind of want the concept of quotient type to be more commonly accessible to like the programming language community, especially the programming language community that's familiar with abstract data types, like the Haskell community, is I think programmers are actually very comfortable with these notions of like term algebras. Like I want to make an abstract syntax tree for some language. And for universal algebra and for a lot of algebra, abstract algebra, this is kind of the secret idea, the core idea. You can even define algebra as the study of make these term languages and then quotient them by these equivalence relationships. So I think programmers actually have a pretty good understanding of term algebras, at least if they're familiar with algebraic data types, but they're not usually that familiar with quotient types since quotient types are pretty rare. So here's just an example of how you can model some algebraic concept with using quotient types. So we have a algebraic data type that's from a programmer's perspective is essentially a syntax for just a language where you have a unit, you can multiply, you can invert, and you have constants of type A. And then we want to create the free group. So in this case, we have all the operations, but nothing says like multiplying A times its inverse will be 1. Like mul of inv of C of 1 is not equal to C of 1. So quotient types allow us to enforce these equations. So we say, for example, mul of x times unit should equal unit times x should equal x. We have the associative law, we have the inverse law. And this allows us to capture the notion of a free group and then notion of groups within the language, work with them as just normal data types. Right now, if you wanted to do something like this in, for example, Haskell, you definitely do this data type T, but then you wouldn't have any way, like these expressions could be interpreted in many ways, and there's nothing enforcing that they should behave like a group. So I haven't actually talked too much about how to use quotient types. As I said earlier, producing values of the quotient type is pretty easy. You just need a value of T. Consuming is where it gets interesting. So if we have a function f that takes T quotiented by this equivalence relation tilde and produces a value of type R, then if we want to apply that function on T, this quotient type, then this is a function defined on values of T, but it's required to satisfy this property that f of x equals f of y whenever x is related to y. And this equality is presumably some kind of behavioral equality. And then one way to understand this is in terms of its elimination rule. This is another little bit of category theory happening here where we're using the duality of quotient types and subset types to say a quotient type, we can eliminate a quotient type by reducing it to a subset type that says for all functions from T to A, we want only those that respect this equivalence relation. And then we can produce a value of type A if we have a function of that form and a value of type P. So from a software engineering perspective, so less theory and more like if I had these in my language, why would I use these? As I mentioned, they separate the two tasks of abstract data types, information hiding and invariant enforcement, into two separate concepts. So now we can have the invariant enforcement part without the information hiding. The invariants are now enforced statically by the compiler instead of with an abstract data type, you have some code that just assumes correct. And one of the benefits of this is since the representation is public, consumers can actually exploit that representation. They just have to convince the compiler that they don't depend on that representation, like the result does not depend on which representation. But as I mentioned at the beginning, since we don't have information hiding, we are actually exposing the representation. So changing representation will change the interface. So now the second part of the talk, which is essentially completely divorced from the first one. So behavioral reflection is a special case of the general notion of reflection that I like to split into two axes, introspection and intercession. So introspection is just being able to read data about the interpretation environment of the code. So this would include runtime type information, type case, listing the methods of an object, listing the modules in a program, etc. Intercession is the right part of that. So this would be like removing or adding methods to an object or changing a continuation to a different continuation. And so on a different axis is structural versus behavioral reflection. And these are kind of fuzzy categories, but structural reflection is what most people think of when they think of reflection. Most nowadays, many even mainstream statically typed languages like C# have structural reflection, including intercession. And so the structural reflection refers to I can manipulate like the natural functional units of the programming language. So I can add and remove methods or classes or modules or whatever. Maybe I can replace a method with a different method. Behavioral reflection is very different. Behavioral reflection is changing the language itself. So in this case, you expose the state of the interpreter and you manipulate that state. So to demonstrate that, let's first define a simple interpreter. This is using the CEK machine, which is an abstract machine for call by value lambda calculus. Straightforward variables, lambdas application, so straight lambda calculus. In practice, you'd want to add like constants and some other stuff to make it a little more practical. But for our purposes, I won't go in detail. I have an article on my site that actually has an interpreter with running code and expands on this. Values are just closures. That's the only thing we have in this, but would include integers and other stuff if we had that. Environments are just list the values, and we have a continuation that will tell the interpreter what to do next. So either we're done, there's nothing left to do, or we have a function that we're evaluating, or sorry, we have an argument that we were evaluating, and when that's done, we want to evaluate the function, and then once we evaluate the function and the argument, we can apply them and continue. The interpreter is very straightforward. This is the entire code. These two slides is everything. I'm not going to go in too much detail. The only thing I really want to talk about here is the type of the CEK thing. And in particular, that has three arguments, the expression, environment, and continuation. The C stands for like code or control and corresponds to the expression part. E is for environment, K is for continuation, because K is always for continuation. And so there's not too much to say about this. This is fairly straightforward. I don't expect you to like read it and immediately understand it, but if you were going to write a lambda calculus interpreter, this is relatively straightforward if you work through it. Like I said, we don't actually need that much here. But what we want to do is actually expose this expression, environment, and continuation as values in the language that we can manipulate and then be able to provide new ones back. So this we do in two parts. We have a Reify, which will take the current environment and continuation. It doesn't actually give you the code because when you call Reify, the only code that would be there would be the call to Reify, so you already know what the code is. But this includes all the interpreter state. To get the code for other parts, we can actually look into the continuation, and we will see like the arguments before they're evaluated. We'll have the code for that. And so this is how this would correspond to introspection. This is how we would see the state of the interpreter. And then reflect corresponds to the intercession. This is actually changing the state of the interpreter. So it just takes the three arguments to the interpreter and installs them in the interpreter. So conceptually, we would want an interpreter that had two extra operations, where Reify just has some lambda that's on or evaluated some value that stands for a lambda, and it just passes the environment and the continuation as arguments to the lambda that we provided. And then we would have a reflect that just takes continuation and an environment code. It's in reverse order because of the convention or pushing arguments in the opposite order, and then it just calls the CEK thing with those arguments. This code doesn't even type check, but it's not too hard to make something that will type check. And before going into combination, one kind of important thing is how much you can do with this depends on how much we expose the representation of the environment and the continuation. So if they're completely opaque, then all we could ever do is use Reify to get a continuation, for example, and then use reflect to replace the current continuation with some other continuation we'd captured earlier. So it's very easy to implement call CC using Reify and reflect, and we can implement mutable state, we can implement quote. Eval is trivial, reflect basically is eval. And so the power we give depends on the representation. So in a worst case scenario, with we're just focusing on continuations for simplicity, is if the continuations are opaque, then we can only replace them. If they're represented, for example, as functions, then we could pass the identity function. We could do something like abort. So we would need a functional representation if we want to implement call with concurrent current continuation. If we expose them as this would, as a bunch of stack frames, then we could rearrange stack frames, replace them with our own stuff. So the more detail you expose, the more powerful the behavioral reflection will be. So what happens when we combine these things? As I said, this is very just kind of ideas and thoughts. This actually came out of a talk I had with, just a conversation I had with Ed Komet after ICFB 2018 on the train ride home, train ride to the airport. So the probably most interesting idea is having a type like this, where we have a type code A that's expressions of type A, but then we quotient by two expressions are equivalent if they evaluate to the same thing, or really you'd want something like the reflect applied to these expressions is equal. And what this leads to the suggestion that we could prove that the type A is isomorphic to the type code A. And if that's the case, that means at any time we could use Reify to turn an expression just at some arbitrary value into its code, and then manipulate the code, and then replace it with maybe a different representation. So maybe we get a function, we manipulate the representation of this function and replace it. And as long as we satisfy this equation, that manipulation would be a pure function. Like we could replace the code with new code, but it would be required to behave the same. So this would dramatically, if we made reflect and Reify have types like this would dramatically rein in their ability to do crazy things. And so we would be able to do stuff like have optimization as like a user-defined library, where you could just at runtime take an expression or a function and replace it with an optimized version based on runtime data, like just as a library function. We can have controlled side effects. We can look through the terms or restrict the continuations to behave in certain ways by either providing certain quotient types or just dynamically checking. And we could allow different behaviors in certain contexts. This is kind of this whole kind of reflecting on code, but simpler ideas, exposing type case without breaking parametricity. We could allow you to reflect on the term, but then make sure that the reflection that you do doesn't actually change the behavior. So you might be able to do something special that's easier to implement and maybe more performant without actually breaking the nice properties of the language. A similar example is continuations are often better behaved when they are linear, meaning they're used exactly once. That's something we could enforce either by a quotient type on reflect and Reify, or again, by a dynamic check. I don't remember, but I remember when I was talking with Ed having other more interesting ideas in this, but I don't remember exactly what they are. But there's a lot of room here where it's interesting what could be possible and how we could add something that's as ill-behaved and as powerful as behavioral reflection to a language like Haskell or Agda or Liquid Haskell, if you want to consider that a separate language. It would be extremely difficult to check the properties in general. So to verify that your function actually is a valid function consuming quotient type would be very difficult. But that's basically where I want to stop. Like I said, I more want to put this idea out there. If you get nothing from this talk, the quotient type stuff is definitely the more important thing and more readily available. But I think this is an interesting idea that, as far as I know, is just hasn't been considered at all before. And so I want to just hopefully spark some people to look into it and play around with it. There's a couple ways to attack it. But that's it.